Hi class, okay. Today we are going to perform the last experiment, qualitative test of organic compounds. So in this experiment, okay, you will know the basic reactions of the different types or different classes of organic compounds, okay, which we have discussed for the whole course. No? So this will give you an idea how to identify a particular compound, no? Whether it is an alkene, alkyne, or whether it is an aromatic compound, okay, or other functional groups as we go along with the experiment. So this is a very important culminating experiment, okay, that will provide you pertinent information as regards to the identification of the different classes of organic compounds. Okay, so one of the important classes of organic compounds are the alkenes and alkynes. Okay, so how are these compounds or these classes differentiated from other classes of organic compounds like aromatic, alkyl halides, etc. Okay, so the first experiment, okay, as you can see, first we have to generate the unsaturated hydrocarbon, no? So in this experiment, we cannot use alkene, no, because the process is not that easy, no. We have to have a special type of reagents, no. But we can synthesize alkyne, no. The result would represent the identification of alkenes and alkynes. The result for alkyne will be similar to alkene. So the first step is to synthesize acetylene gas. Okay, so acetylene gas is synthesized by reacting calcium carbide or calboro in layman's term with water. Okay, so this is our calcium carbide, as you can see it is in the glass, no, and we have to react this with water. Okay, the reaction will produce acetylene, no, which is a gas. So we have to collect the gas, no, by water displacement. Okay, so the byproduct of the reaction is actually calcium hydroxide plus, which is white, and it is also called lime, no, which has medicinal application also, no. It can be a neutralizing agent also. Okay, so here, how is the acetylene produced? No, so here you have the calcium carbide. The water is added drop by drop, no, not up drop, because it will generate a lot of acetylene gas and it might explode, no. So that's why in the synthesis of acetylene, okay, you have to be very careful, no, that you are just adding the water drop by drop, and the gas, okay, will come out here. So we have to use the, okay, so you have the collecting test tube. We have to fill this up with water because we're going to do the water displacement, no? So fill this up completely with water, and the rubber tubing should be underwater, okay, like that, no? So it is now ready to, once the gas is produced, okay, this will displace the water inside the test tube, and then we have to cover this immediately with the cork, no? So let's see if we can do this. Okay, so I'm now going to open this one. So I think we have the water already coming out. So hopefully we can produce the gas. There, I think we have the gas already. Okay, so we have collected already our acetylene gas. No? At first we have a difficulty of collecting it, but it's okay already now. we move on to the first test, no? Before we go to the test for unsaturation. So the first one, okay, is ignition test. Okay, so this is one way of identifying, okay, alkane. Okay, in our example, we have alkane versus aromatic. So for alkane, we have hexane as our compound, and for aromatic, we have benzene. So how could you differentiate alkane from aromatic? By ignition, okay? Because as you know, alkane has a lot of hydrogen. Any material class that has a lot of hydrogen is highly combustible, okay? While those that do not have or less hydrogen, okay, is less combustible. So we would expect here that benzene, since benzene or aromatic has less hydrogen and more carbon, we will observe a lot of smoke, okay, compared to alkane. So let's see if we can observe that in the experiment, okay? So we do what we call ignition test, no? So we have to use the evaporating dish, and then we're just going to place 3 drops, no? To avoid, fire, no? Because we are burning this one. Here we have the hexane, no? We're going to place 3 drops here. And here we have benzene, also 3 drops. So this is our reagent, hexane, it's a liquid, okay? And we have our aromatic, benzene, which is also a liquid, okay? So we're going to place 3 drops, okay? So first, we have hexane, and observe the flame as well as the smoke. Okay, so this is hexane class, no? So observe. Okay, so that is hexane. Observe the flame. Okay, that's it. Now let's go to benzene. We're going to place 3 drops also. Okay, observe the flame and compare. Now you see that? Okay, you see the difference now? You have a lot of carbon for benzene. Okay, so that's it, no? For alkane versus aromatic, you can differentiate them from their ignition test. Okay, so now let's move on to the test for the presence of double bond. Okay, we have defined unsaturated and saturated hydrocarbons, right? Okay, unsaturated would be alkenes, alkynes, and aromatic, while saturated would be the alkane. No? And for this, okay, second part of the test, okay, you will know how to identify the presence of alkene and alkyne, no? By the first one, okay, as we discussed in the lecture, we have decolorization test. Okay, alkenes and alkynes undergo electrophilic addition reaction class, no? And one type of electrophilic addition reaction is bromination reaction. Now bromine has an orange color, no? Sometimes reddish brown color, no? So when bromine reacts with alkene or alkyne, the product is alkyl halide, no? So the bromine is integrated in the alkene and alkyne, forming alkyl halide. So what will happen to the color of the bromine? Okay, it will disappear. That's why it is called, the test is called decolorization test, no? So when the color of bromine disappears plus, it means to say that it has your unknown compound is either an alkene or alkyne, no? Aromatic will not undergo electrophilic addition reaction, okay? So the color of bromine will remain the same, okay? That is how you are going to differentiate aromatic from alkene and alkyne, no? So in our experiment, we have our acetylene, to represent the unsaturated hydrocarbon alkyne, no? And then benzene for aromatic. And let's see the difference in the reaction. Okay, so we have this is the acetylene that we have collected. Of course, you cannot see the gas. There is still water here, no? Because I was not able to completely remove the water, but it's okay. The gas is above, no? So you will see the color of the change in the color of bromine. So this is our bromine water. Okay, so you notice the color of bromine class, no? It's yellow, no? Supposedly it's yellow orange, but you have a very low concentration of bromine, no? So let's see if this will turn into colorless, no? After the reaction with acetylene. Okay. Okay, let's check. Okay, so if you compare that with this one plus, okay, you could see the difference, right? Okay, the color of bromine disappeared. Okay, so meaning it has reacted with acetylene gas. Okay, so let's compare this with aromatic. Okay, this is benzene plus, no? So let's see if we add bromine, no? If there will be a change in color. No? So we're just using a very small amount of benzene because our bromine is not very yellow. No? We might not be able to see the difference. So let's see, okay, if the color will be the same. So of course, they will not mix. So if you notice, okay, look at the color, okay, of the benzene layer. It's still the same, no? Look at the color. This is the color, okay? So compared to acetylene, it's really colorless. But here you can still see a shade of yellow color for the benzene layer, no? Indicating that it doesn't react with bromine. Okay, so that's it. Now, another important test, no, for alkenes and alkynes to differentiate that from alkane and benzene, no, is the Bayer's test. Okay, the Bayer's test is the reagent for Bayer's test is actually potassium permanganate or KMnO4. Okay. It is a very strong oxidizing agent. So, potassium permanganate can oxidize alkenes and alkynes to carboxylic acid. Okay? So, it will break the carbon-carbon bond, but not the alkane and the aromatic. Okay? So, the byproduct, okay, for the reaction of Bayer's test with alkene or alkyne class is manganese dioxide, which is chocolate brown. Okay, so if we can observe this chocolate brown, which is MnO2, it means to say that the experiment, okay, is positive for the presence of either alkene or alkyne, but not if it is if you don't observe MnO2, it means to say there is no oxidation, there is no reaction. And that will be observed for alkane and benzene because they don't, this kind of hydrocarbons cannot be oxidized by potassium permanganate. So let's see. So here, okay, let's start with acetylene. So this is our acetylene gas with small amount of water, so don't worry about that. Now we're going to add the Bayer's test or the Bayer's reagent, which is potassium permanganate. Just 2 to 3 drops plus is enough, no? But you have to do this fast, no? Look at how I open the fork, no? I have to place the KMnO4 right away because the acetylene might escape, no? Okay, so let's see if our experiment is successful. Potassium permanganate is purple. And see if there is a change in color, okay? So you see that change in color. Compare that to, if you have a lot of acetylene plus, you will observe chocolate brown. No? Maybe we can there is also this. There is already a change, no? If you compare that with, you see that brown? That's positive already. See, it's chocolate brown. Potassium permanganate is violet, as you know. Okay, as you can see here, this is your potassium permanganate. No? You can see the difference in the color. Okay, so this is positive, no? For the presence of acetylene. No? Let's try one more. No? See that? No? So you see that precipitate? You see that brown precipitate plus? That is MnO2. Okay? So now let's see for hexane, which represents alkane, and benzene for aromatic. So this is hexane, okay? And we're going to place a few drops, okay, of hexane and observe, no? 1, 2, 3. See? You still have that violet color, okay? Compare that with a result for acetylene. See the difference, okay? So the violet is still there. That means potassium permanganate cannot oxidize hexane. Okay. So now let's go to aromatic benzene. So what have you observed? It is similar to hexane. There is no reaction. Okay. So only the unsaturated alkyne reacted. So therefore we can differentiate it from alkane and aromatic. Okay. So that's it for Bayer's test. Now let's go to test for alkyl halides. Okay, so you know alkyl halides have halogens. Okay, so how can we identify alkyl halide? Okay, so one important reactions for alkyl halide, okay, is the reaction with silver nitrate. No, when silver nitrate reacts with alkyl halide plus, it will remove the chlorine, bromine, or iodine. No? So if it is alkyl chloride, the silver ion will react with chloride. Okay, you know that in your inorganic chemistry, right? Okay, silver will precipitate chloride, forming white precipitate. Okay, so in this experiment, so we're going to use ethyl bromide, okay, as representative for the reaction of alkyl halide. Now, so therefore, since we are going to use silver nitrate, okay, our precipitate will be silver bromide, no? And silver bromide is not white plus, no? It is the silver chloride that is white. Okay, silver bromide is what do you call this? Dirty white. Okay, this is silver nitrate, no? And then we have ethyl bromide. So where is ethyl bromide? There. Okay, so this is ethyl bromide plus. Okay. So we have now the complete reagent. So you just have to place a few drops. So you have now ethyl bromide, no? And we're going to react this with silver nitrate. So we have to swirl. Okay. The precipitate is not very clear, but you see the color, it's dirty white plus, right? We have to heat this one, no? In a water bath to really, but we can observe already, look at that, no? Even without heating, you see? The reaction is very slow because we are not heating it. But if we're going to heat this, okay, we can observe the white, the creamy, no? Dirty white as what I described. No? It's let's try to heat this one class if we can observe more precipitate. Alright, so this is after heating class. If you notice, okay, we have now the precipitate, no, of silver bromide. So you see, try to check the correct color, no, in the Google, no, of silver bromide. So as you can see, it's not completely white. Silver chloride is white plus. but silver bromide is a little dirty white, as you can see. Okay. Let's compare okay, that is for test for halogens. So now let's go to Bellstein test or flame test. No? So I think we have done this, no, in your inorganic chemistry. So let's see. We can also test the presence of halogen by heating, no? Halogen containing compounds like alkyl halide. So in our experiment, we are going to use ethyl bromide, okay, and observe the change in the color of bromine. Okay, it could have been better if you have ethyl chloride. Okay, so let's see, observe the change in color of bromine, no, by flame test. Okay, so this is our inoculating loop. Okay, so we just get small amount, no, as a film, no, here. And then we're going to heat this one, okay, using alcohol lamp. No? Okay, so this is our ethyl bromide. Okay, so let's watch carefully, no, if there is a change in the color of the flame. Okay, observe the first color. No? Okay, see? Do you see that, class? Again. See that? Now let's go to test for alcohols. Okay, we classify alcohol, remember class, as primary, secondary, and tertiary alcohol. Okay, example of primary alcohol is ethanol. Secondary alcohol is isopropyl alcohol, and of course you have tertiary butyl alcohol. So how are these three alcohols differentiated? We can differentiate them first by Lucas test. Lucas test is a mixture of zinc chloride and hydrochloric acid. Okay, and if you recall in our lecture, one of the reactions of alcohol is nucleophilic substitution reaction. Okay, and if we react alcohol with hydrochloric acid, okay, the product is alkyl halide. No? So for ethanol, we have ethyl chloride. For isopropyl alcohol, we have isopropyl chloride. For tertiary butyl alcohol, we have tertiary butyl chloride. Okay? So all of this, okay, will form alkyl halide. And you know that one of the properties of alkyl halide is that they are insoluble. No? Insoluble in water. Okay? So in these reactions, if we observe an immiscible layer, if we observe a layer, because alcohol has no layer, no? But once it reacted with hydrochloric acid, since alkyl halide is not soluble in alcohol and water, then we are going to observe a layer, like oil and water. Okay? So if there is a layer, it means to say alkyl halide is formed. Okay? But we can differentiate these three types of alcohol depending on how fast the formation of the layer. Okay, so observe which of these three alcohol will form the product at the fastest rate. No, because you have primary, secondary, and tertiary. No, so you should be able to explain, no, which one is the slowest and which one is the fastest. Okay, so you have to record the time. In this case, no? Record the time how fast, no, the layer is formed. So let's start with tertiary butyl alcohol. Okay, so we're going to place just a few drops, no, 10 drops in this case, and then we're going to add Lucas reagent. Okay, the role of zinc chloride plus it serves as a catalyst, no, it will enhance the reaction. So let's see, we'll add also 10 drops of this one. Okay, observe. I'm going to swirl, no? And there should be a layer, no? Or if there is no layer, the solution turns cloudy. So you record the time, no? Okay, we'll let it stand. Theoretically, supposedly after 5 minutes, may 5 minutes. Okay, so let's go to secondary alcohol. So, let's start the time for this one. We'll let it stand also, no? And see which one is longer, isopropyl or tertiary butyl. So let's check our tertiary butyl. There's no layer yet. Okay. So let's go to primary alcohol, ethanol. So let's see. No? So we let it stand. Okay, this is after 5 minutes, no? Okay. Look at the tertiary butyl chloride, it's very clear, no? So that means it's the fastest, no? Your isopropyl, which represents secondary alcohol, okay? It's cloudy already, no? But it takes a longer time compared to tertiary. And look at the primary. Your ethanol has not changed yet. See? Okay, look at the tree, no? If we're going to compare the tree now, okay? Look at the ethanol or primary alcohol, okay? It's not as cloudy as isopropyl alcohol, not as clear as tertiary butyl alcohol, okay? So in other words, the ethyl alcohol, okay, the primary alcohol exhibited the slowest reaction, okay? While the tertiary exhibited the fastest reaction in this case, okay? So you should be able to explain why tertiary, okay, can easily undergo substitution reaction compared to secondary faster than primary. That is the sequence, okay? So that's it. Okay. So the next test, okay, the first test for alcohol is its reaction with Lucas reagent class, no, to form alkyl halide. Now, the second type of qualitative test for alcohol is oxidation process, okay? So in this case, we are not going to use Bayer's test. We are going to use another strong oxidizing agent, which is potassium dichromate, okay? The color of potassium dichromate is due to its metal, okay? You know that in your inorganic chemistry, that salts have different colors due to the presence of the type of metal, no? So for example, in potassium permanganate, it's violet due to manganese, no, with an oxidation state of +7. In potassium dichromate, the color is orange because chromium has an oxidation state of +6. So highly oxidized metal, okay, are very good oxidizing agents, no? So take note that oxidation, okay, is a redox reaction. So if one is oxidized, another one is reduced, okay? So if potassium dichromate acts as an oxidizing agent, it will oxidize alcohol to carboxylic acid if it is primary alcohol, ketone if it is secondary alcohol, and nothing will happen for tertiary. What is the basis for this class? Why primary alcohol and secondary alcohol can be oxidized? Oxidation means removal of hydrogen, no, at the primary carbon and secondary carbon. In primary alcohol like ethanol, there are two hydrogen that is attached to carbon containing the OH. So therefore it is oxidizable. In isopropyl alcohol, there is one hydrogen at the carbon containing OH, so it is still oxidizable. But in tertiary class, there is no hydrogen at the carbon containing the OH. That's why it cannot be oxidized. Okay? So which one can easily be oxidized? Of course, those that have a lot of hydrogen, and that is ethanol. What is the product for primary? It will be carboxylic acid. So if it is ethyl alcohol, you know what will happen to ethyl alcohol if it is oxidized to carboxylic acid? You should know that. How about for secondary alcohol like isopropyl? There is only one replaceable hydrogen. So do not expect a secondary to become carboxylic acid. Okay? For secondary alcohol, it will be converted into a ketone. Okay? So particularly acetone. For primary, it would be acetic acid. Okay? So let's see what would be the visual result. Okay? to find out whether oxidation has happened. No? Now here, you are going to observe the change in the color of the oxidizing agent. Potassium dichromate is orange, okay, if chromium is positive 6. Once it oxidizes the alcohol, it will be reduced to chromium plus 3, okay? And the color of chromium plus 3 plus is green. So if the color of potassium dichromate changes from orange to green, it's an indication that your alcohol has been oxidized. If there is no change, then there is no oxidation that happens. Okay, so let's see. Okay, so we have here ethanol, isopropyl alcohol, and tertiary butyl alcohol again to represent primary, secondary, and tertiary. And we have our potassium dichromate. Okay, so if we're going to check this is orange, no? Under acidic condition. Okay, so we're going to this is our, let's start with tertiary butyl alcohol. So we're going to add, this is 10 drops, and we're going to add 10 drops of potassium dichromate. Place this in a hot bath, no, to see whether there will be a reaction. So that is tertiary. Now let's go to secondary, which is our isopropyl alcohol. Okay, so we have 10 drops already of isopropyl. So we just have to add 10 drops of potassium dichromate. So this is potassium dichromate. Okay, shake and then place in the water bath. Okay, so that is heated at about 70 to 80 degrees plus, no, not boiled. Now we have ethanol to represent primary alcohol. Shake, shake, shake. Okay, so this is our primary. Okay, so let's see after 5 minutes. If the color will change to green, that means your chromium plus 6 has been reduced to chromium plus 3 and your alcohol has been oxidized. Okay. So next is you have, while waiting for that one, we can move on to the next experiment, test for phenols. Okay, phenols are aromatic compounds plus. Okay, and the test is very important, no, because phenol is a representative of natural products called flavonoids. Flavonoids are phenolic compounds plus, no, that are synthesized by nature, no? And it is one of the important natural products because flavonoids, okay, or phenolic compounds are antioxidants or anti-cancer agents, no? They can remove radicals from the environment, like hydroxyl radical is one of the most dangerous radical in the environment, okay? So that's why we take antioxidant drugs like vitamin E, vitamin C. These are antioxidants. Now, if you don't want synthetic drugs, then you can resort to natural products. Okay, you can eat compounds, no, flavonoid-containing compounds. Okay, fruit has a lot of flavonoids, no, so you can use that, no, if you don't want synthetic drugs, okay, as antioxidants. Okay, so how are we going to identify the presence of phenols or aromatic compounds? There are two tests that we're going to do. One is ferric chloride test. Okay, the ferric chloride will react with phenol to form complex compounds, so we'll observe various colors. Okay, the second one is millions test. Okay, the millions test contains mercury, no? Mercuric ion as one of the major component of millions test. Okay, check the reagent, no? Kasi this comes out in the board exam class for pharmacy. Okay, so for phenolic compounds, millions test will give a bloody red color. Okay, so let's see if we can observe that. Okay, so here, okay, let's check with, let's start with ferric chloride test, okay, and observe the color. There is a change in color right away. Okay, so record the change in color. Okay, It's a little bit purple. Okay, so there is actually a combination of colors here, but the one that is very prominent is what? Indigo, right? Indigo. Okay, and let's go to the second test, millions test. Huh? So we're going. Let's see if there is a change in color. We cannot observe the change. Okay, maybe we have to hit this a little bit. Let's see. Right. So here's the millions test class. So you'll notice the change in color. Okay. So that's red. No. Wine red. Actually, if it's concentrated, it's bloody red. So it's wine red, no? For millions test, okay? So that is test for phenols. Now, okay, so this is primary alcohol ethanol class, okay? So observe the green color when I shake this one, huh? Okay.
Shake.
Okay, so you see that the green color, light green color, okay? That is for primary. Compare that to tertiary. This is tertiary. Look at that, okay? Okay, you have, this is tertiary alcohol. This is primary alcohol, okay? You see the color, and this one, look at that, okay? The orange color in tertiary, okay, is very prominent compared to ethyl alcohol. Okay. Now, if you compare isopropyl alcohol, it's very obvious, no? It's cloudy already. So that means it is oxidized to ketone. For secondary ketone, for primary carboxylic acid. Okay. So our next test class, okay, is for aldehydes and ketones. So this is another class of organic compounds, okay? You have to take note that aldehydes are oxidizable because there is still one hydrogen left in the C double bond O, okay? Or carbonyl group, we call that. For ketone, there is no hydrogen left. That's why we can easily differentiate aldehyde from ketone by oxidation, no? Because aldehyde can be oxidized, ketone cannot, okay? And some of the important tests, no, for differentiating aldehydes from ketone, okay, in terms of oxidation is Tollens test, okay? The reagent for Tollens test is silver, okay, amino complex, okay, or basic solution of silver nitrate plus, okay? So when you react Tollens reagent to aldehyde, your aldehyde will be oxidized to carboxylic acid and the silver ion will be reduced to silver metal. So you will observe a mirror. So that's why it is also called silver mirror test, no? Because you will observe a silver mirror on the side of the test tube, no? It's shining. Ketone will not, because it cannot be oxidized. Okay, so that's one way of differentiating aldehyde from ketone. Another one is Benedict's reagent. Okay, the active reagent in Benedict's reagent is cupric sulfate class. Okay, and this is a basic reagent. So you know cupric sulfate will precipitate as cupric hydroxide. No, so in order to prevent the precipitation of the reagent, it is added with what you call a chelating agent. No? A chelating agent is a compound that will prevent the copper ion to precipitate so that it will react with your organic compound. So there are two oxidizing agents for that. You have what you call Benedict's test and Felix test. No? The active reagent is copper plus 2, no? In the form of cupric sulfate, which is blue. No? But they differ in terms of the chelating agent. Benedict's reagent has its chelating agent is sodium citrate, no? while the Fehling's reagent, its chelating agent is sodium potassium tartrate, or it is also called Rochelle salt. Okay, so they are used to prevent the precipitation of copper plus 2. So once you add this reagent to aldehyde, it will your copper plus 2 will be reduced to copper plus 1 in the form of cuprous hydroxide, or Cu2O. Its color is brick red. No? So once you observe a brick red precipitate, it means to say that there is an aldehyde. No? Ketone will not react. Okay? So you will not observe brick red precipitate for ketones. No? So that is for oxidation process. Now, another important test for aldehydes and ketones is you have the reaction with DNPH. You call that 2,4-dinitrophenylhydrazine. Okay, the reaction is nucleophilic addition elimination reaction plus, no? And the expected product is a reddish orange precipitate, no? Now in this case, since aldehyde and ketone have carbonyl group, both will react, no? But they can be used to differentiate other carbonyl containing compounds like carboxylic acid derivatives, no? They also have carbonyl group, but they will not react with DNPH, no? So this test is used to differentiate aldehydes and ketones from other carbonyl containing compounds like ester, amide, anhydride, or acyl halide. Okay, but both of these will react. No, will give a reddish brown precipitate. No. Now another one is the bisulfite test. So you react your aldehyde and ketone with sodium bisulfite, and you will observe a white precipitate. Both will react plus positive. No, but again, they can be used to differentiate from other carbonyl containing compounds. But if you want to differentiate aldehyde from ketone, you either use Tollens reagent, Benedict reagent, or Fehling's reagent. Okay, so let's start the experiment. Let's start with DNP. So our test reagent is benzaldehyde to represent aromatic aldehyde, acetaldehyde, okay, and then you have acetone to represent ketone. Okay, so this is our DNPH. So we're going to add 10 drops of this one. So I'll just place it here plus, no? Okay, now we need heating, okay, for this. But if you notice plus, okay, even without heating, your aldehyde is very reactive, you see? It already reacted, no? Forming that precipitate, that cloudy color is precipitate. But the other two, no, acetaldehyde and acetone, we didn't observe any change yet, no? So I think for acetaldehyde, it turns cloudy already, as you can see. No? But benzaldehyde is very reactive, as you can see. No? So we'll heat this a little bit, no? Because it needs a little heating. Okay, so we'll check that for a while, no? After a few minutes. No? Okay, so while waiting for the reaction, let's go to the next test. The next test is your sodium bisulfite. Okay. So we expect a white precipitate here. Okay, so you have to check the reaction. Okay, so this is our bisulfite test. This is our sodium bisulfite. Okay, so let's see what will be the reaction. Okay, for the 3 aldehydes and 1 ketone, acetone. So shake. Okay, we're expecting white. You see? We already have the solid form, no? So that is for benzaldehyde, okay? So that white precipitate is the salt, no? Look for the reaction, okay? You have to look for the reaction of sodium bisulfite with aldehydes and ketones. So this is our acetaldehyde. The solution turns cloudy already, indicating the presence of precipitate. Okay, as you can see. Now, the last one is you have acetone. Okay, you see? Okay, you also have the cloudy color. Okay, so all, no, that is also white. Okay, so all are positive to sodium bisulfite. Okay. Alright, so now let's go to oxidizing agents. So we only have two oxidizing agents here, Tollens and Benedict's. We don't have Fehling's reagent, okay? But this is enough to differentiate aldehyde from ketone, okay? So let's start with Tollens reagent, okay? So let's add 10 drops of this one, Tollens reagent. Alright, so okay, you have fast reaction here. Alright, so we'll hit this one, no? So that we can observe the silver mirror. Okay, we should be able to observe that mirror. No? So this is the result for acetone. No? So you notice that orange color plus. Okay. So that's positive test, okay. This one, okay, is supposed to be positive, but we didn't observe that precipitate, no? Okay, maybe it will take a longer time, no, for this to react, no, compared to acetone. The acetone is very fast class, okay. So you just let it stand. Okay, so this is the Tollens test class, okay. So there should be a mirror here, but it is covered with the black, no, solution, but you can see at the bottom, okay, it has to be shiny. The test tube is supposed to be, there should be coating, no, at the bottom, no, you should have silver deposited, no, so you see, okay, it should glitter, no, there. Same thing here, okay, you notice at the bottom of the test tube you already have that mirror there, okay, indicating the formation of silver, okay. Here it will take more time for acetone to develop the silver mirror, okay, but we already observed that for the other two. So we are expecting this to be all positive, okay. Okay. So if you notice class, okay, because of the color of the solution, no, but you will notice the silver sticking on the side. You let it is implying, okay, that portion there, no, okay, di masyadong makita lang class dahil sa solution ng black, no, but that shiny coating the test tube is the silver, okay. So just okay, so now we move on to Benedict's reagent class. Okay, so we're using benzaldehyde, acetaldehyde, and acetone again. So we're expecting brick red color. Okay, so we're going to. Okay, you notice there is a reaction already class, no, for this one, acetaldehyde. Okay, you already have a small amount of red. For this one also for benzaldehyde, okay. Now we don't expect it for acetone, so you see. Okay, let's see if we can produce more of that if we're going to heat this one. Okay. Okay, so you notice the acetone class has no change in color, but benzaldehyde and aldehyde, no, you have that change in color indicating the positive tests. Okay, for aldehydes, but not for ketone. Okay. Okay, so we move on to the last test class, test for carboxylic acid derivatives. Okay, so what are the carboxylic acid derivatives? You have acyl halide, anhydride, esters, and imine. Okay, so here we're going to test for esters. The process is called esterification. Okay, and you know esters are produced from the reaction of alcohol and carboxylic acid, resulting into the formation of a pleasant smell. Okay, so smell from flowers, fruits are esters, no. So that's why they are extracted, no, as component for perfume. Okay, so how is this done? Okay, so you react your alcohol, in this case ethanol with acetic acid, okay, in the presence of an acid catalyst, sulfuric acid. So we add 3 drops of that one, okay, and your reactant carboxylic acid has a pungent smell similar to amines, no? But once the product is formed, it is converted into a pleasant smell. So if we can smell that the ester, like smell of plastic balloon, if you know what is plastic balloon, okay, then that is the smell of the ester. No? So pag na-form na yan, it means to say that, okay, ester has been synthesized, okay, from the reaction of ethanol and acetic acid. Okay, so here we're going to place 10 drops of the reactants. So this is your ethanol, this is your acetic acid. Okay, so we're going to place 10 drops, okay, of ethyl alcohol. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then we'll mix this one with acetic acid. Okay, you know acetic acid, okay, just like vinegar, has a very strong smell. 1, 2, 3, 4, 5, 6, 7, 8. And then we're going to add 3 drops, no, of the catalyst, no, sulfuric acid. So we add 3 drops of concentrated gas. So you have to be very careful with acid, especially sulfuric acid. There, no? So we're going to place this in a water bath, no, to enhance the reaction, and then cover this with a marble to prevent evaporation of your reactants. So there, okay, and then we first esterification. So esterification is synthesis of ester. But we can also break down ester into its component reactants, okay, alcohol and carboxylic acid. The process is called hydrolysis of ester, okay. So we can break the ester by adding water in the presence of the same acid class, no? So in other words, the reaction is reversible, okay. Now, we can hydrolyze ester under acidic or basic condition, okay. Under acidic condition, we produce alcohol and the corresponding carboxylic acid. But under basic condition, your carboxylic acid will become salt. Okay? So if it is acetic acid, your product is sodium acetate. No? So you don't expect that smell, no? If it is under basic reaction. You use sodium hydroxide to break the ester. No? But basic hydrolysis plus is very important, especially if the ester has a very long carbon chain, no? Like for example, oil, no? Oil is triester, no? Not only monoester, but triester of glycerol, okay? So if you hydrolyze oil by adding sodium hydroxide, okay, the salt product is what you call the salt, okay? So that's why oil can be a very important material for the production of soap, okay? So you just react that with sodium hydroxide, no? And then you will observe white precipitate, which is actually your soap. The other product is alcohol, which is glycerol, which you can also separate. And you know glycerol, in pharmaceutical preparation, it is used as moisturizing agent, no? So glycerin is glycerol, no? The one that is present in Vaseline, for example, okay? So here we're going to do hydrolysis under acidic condition, no? Basic condition, by the way, basic, okay? So we're going to use sodium hydroxide, okay, to hydrolyze our ethyl acetate, that is our ester. So we have ethyl acetate here, This is the ester, okay, that we're going to hydrolyze using sodium hydroxide. And then we have sodium hydroxide, okay, 5 drops is enough for this one. Okay, so here we cannot observe a precipitate plus because we have water in sodium hydroxide. Okay? And you know sodium acetate is soluble in water. So that's why we cannot observe, no? But we can observe the smell of alcohol because the other product is ethyl alcohol. And you know the smell of ethyl alcohol, okay? So we cannot observe any change in color, but Ma'am Laika will smell. Ma'am Laika, check if there is a smell of ethyl alcohol.
Meron daw.
Okay. So, according to Ma'am Laika, there is a smell for ethyl alcohol. Let's see. There is, okay? Ma'am Ron? Yes, okay? So, there is ethyl alcohol. So, you have hydrolyzed ester. Now, for the esterification, dapat, okay, I think this is enough. We should be able to smell the ester. Huh? Okay. Ma'am Laika, para walang bias, okay? Wala, malis na eh. Naamoy na.
Namin. Sininghot lahat
Naamoy
eh.
na ni Ma'am Laika lahat yung ester. Dapat ganyan na. Ganyan pag nag-amoy ng chemicals, no? Should be quite far from your nose, no? Alright, so that's it, class, no? So that ends the experiment. Thank you.